Hi everyone, my name is Fabio Ferreira, and today I will bring you a presentation about computer vision. So the title of my presentation is From Pixels to Understanding, an Introduction to Computer Vision. I brought you the following agenda for today, so I will start with a small introduction of myself. We'll then deep dive into the understanding, then go to the fundamentals of computer vision. I will also show you some advanced applications, and afterwards also conduct a demonstration. Yeah, we'll then leave you some time for questions if there are any. Right, about me, yeah, my name is Fabio Ferreira, as I mentioned, not a big typical German name, as you can see, so I have a Portuguese background. I'm living more than 20 years in Germany. I'm married, I have 2 kids, 2 sons. I have a background in computer science and artificial intelligence, and I'm a machine learning engineer and technical lead at ZF Group, an automotive, German automotive supplier. Right, let's go directly into the understanding. So what is computer vision? I think in general there are a lot of definitions, and you can pick your favorite, I guess. I like this one. It's from Antonio Torralba, an MIT professor, and he says the goal of computer vision is to convert light into meaning. And I think it's quite broad definition, but it actually brings into the point. So basically everything you can see is light. So it's really about converting light to meaning. So maybe a little bit different. So what is actually the goal of computer vision? And the goal is to replicate what we humans can see and our perception, and make machines able to analyze, interpret, and also make some sense of images, and of course also videos. I'm pretty sure you might also have seen something like this. So how can we put computer vision into this Venn diagram? So we have artificial intelligence, we have machine learning as a subset of artificial intelligence, we have deep learning, a subset of machine learning. And I would say computer vision is something in between. So we have a strong part of computer vision, and I think nowadays, I think it's state of the art to do computer vision with deep learning. But, and we will see in a few slides, there is also a background of computer vision without deep learning, without machine learning, so traditional computer vision. What are the subdomains of computer vision? So we have, first of all, image processing and pre-processing, basically, yeah, extracting details of low-level details and features of images. We have feature detection, so I don't know, detecting things like edges, corners, shapes, and so on. 3D reconstruction, so basically creating 3D models out of objects of 2D images. And we have also image recognition, basically recognizing something in an image, object detection, segmentation, so that's basically the picture or the video you can see here. So basically, yeah, make a segmentation of certain parts of the image. So what are those parts? And also motion analysis. So why is visual perception actually hard? So if you take a look at this picture, it contains actually quite a lot of information, right? So we can directly see, okay, something very, very bad went wrong, right? So we see a train, and we can directly see, and there is also kind of emotions connected to an image. So you can directly see that maybe, I don't know, something died or whatever. But what the computer actually sees is only the left side, right? So we just have a matrix with numbers. And the real world is just so complex, much more complex than what we can measure in images. I think that's really the hard part about computer vision. So what are further challenges of computer vision? So first of all, it depends a lot of the viewpoint. So if you take a look at these images, it's all the same image, but from different views or viewpoints. And dependent on which image you are looking, it looks actually quite different, even though this is really the same image. Illumination is also a challenge. So you can see on the left side, you can see most of the details of a person, and the same image with just a slightly different illumination from the side, and then you can not even recognize the same person. So that's definitely a challenge. We have occlusion, so basically when parts of an object are occluded in the image. We have also scaling. I'm pretty sure you know, you have seen something like this before. So it's yeah, also a challenge for computer vision. And I think maybe my favorite intra-class variation. So you have stuff like you don't even know how to categorize it. So is it a chair? Is it a table? I don't know, something like in between, maybe. Exactly. So these are the main challenges of computer vision. I mean, there are much more challenges. So of course, that are just a few of them. Yeah, let's go to the fundamentals of computer vision. Don't worry, I will not get too much into the mathematics. That's actually not my goal. I think my goal is just to give you a little bit of understanding what are the basic operations of computer vision. Let's start with image representation. So basically, as I said before, and we saw the picture of this train. How can we represent an image in a computer? So here we can see an image on the left side, and you can see basically every square is a so-called pixel. And on the right side, you have the representation in a computer, let's say. So it's a matrix of numbers, and each number goes between 0 and 255. And a 0 basically means black, or black, and then 225 just means white in this picture. So that's the basic representation. And now the question is, okay, but what about colored pictures? And that's basically the same, just we have, instead of one matrix, we have 3 matrices. One for red, green, and blue. And in that way, we are able to represent an colored image. Right, image preprocessing and feature extraction. So what are fundamental techniques to extract relevant information? Let's start with brightness and contrast. So these are all operations that you can conduct on an image to, first of all, preprocess, and then afterwards extract meaningful patterns out of this image. Brightness, of course, you can adjust brightness and contrast. You can also do something like histogram equalization. You can normalize the color of an image, and you can also apply filters, and I will come to that in a second. And let's take this example. So here we have an operation called convolution, and basically what we do is we have this input image on the left side. And let's start with the right upper one matrix. Basically, we just slide this matrix through all the parts of the image, and we just multiply those values with this matrix. And what we get is basically the vertical edges of the image, as you can see. On the bottom right side, you can see a slightly different matrix, but the same principle. So you just slide this kernel, it's called kernel, through the image, and then you get horizontal edges. So if you combine those two, then you get all the edges of an image. So, and you can already, with such an operation extract a lot of meaningful information from an image. These are just 2 operations. I mean, there are so many operations out there that you can apply for feature extraction. I think this is just a small example. Let's get into a little bit of an evolution of computer vision, and I just brought you some example. So let's say our task is your boss just tells you, okay, build a classifier for classifying or detecting dogs, in this case Chihuahuas, and basically you have an input image, and so we are talking about traditional computer vision here. before artificial intelligence, before deep learning, and so on. And what we see here is basically the pipeline. So you have an input image, and then you have someone sitting there manually and writing feature extractions, writing rules on how to pre-process this image. These outputs are then fed into a so-called role-based classifier, where you really code all the rules handcrafted, and you just say things like, okay, if it has 2 eyes and a nose and it looks like a dog, then maybe it's a dog, something like that. And then the classifier will just raise an output. Okay, is it Chihuahua or is it not a Chihuahua? So what's the problem here? The problem here is that basically it's a lot of manual work, right? So you need to extract, you need also a lot of domain knowledge. So you need to know which features to extract, which rules to write. And then you get new inputs. And then if you look at this, so I think you would agree that some of these pictures are not Chihuahuas actually, but a muffin. And then you will get back to your desk and you will write new features and try to write new rules to classify this image. Of course, this is very painful. And then fortunately, with classical AI and with machine learning, we were able to just replace this manual classifier or this rule-based classifier and just introduce something like a neural network. Here, I just called it very generic classifier with shallow structure. And basically so you still have to do manual pre-processing and manual feature extraction, but you don't have to write the rules anymore. So it just learns from itself, from the data, which rules to apply to classify this image. But then, your boss just comes into your desk or to your office and just says, okay, now we are able to classify Chihuahuas. What about sheepdogs? And you can see it's actually not that easy to distinguish a sheepdog from a mop. And I think at this point, it's exactly the point where you just write your resignation letter and then you just try some new job maybe. But fortunately, again, with better hardware, with the rise of deep learning, we are just able to replace those steps with a so-called deep learning model. And we have, let's say, an end-to-end approach. So basically, we don't have to do feature extraction or manual feature extraction anymore. We don't need to write rules anymore. We just have a model that does feature extraction by itself and is able to classify those images. I will explain a little bit more in detail this deep learning or the state-of-the-art computer vision models. But before that, I would just like to introduce again a little bit more into detail what is actually a convolution. So you may have heard about convolutional neural networks for computer vision. So what is actually a computer vision? And as I mentioned before, it's basically the same as in the edge detections. You have your input image here called here on the left side. In the middle, you have your kernel. And what you do is basically you just slide your kernel through the parts of the image. You just multiply all the values of the kernel with the input image, and then you get an output. And that's basically a convolution operation. And that's basically also what happens in a convolution neural network. But of course, you don't have to write the values of this kernel by yourself, or you don't need to find out which operations do I need to do. The network is able to find it by itself, which operations it needs to be learned to classify, in that case, a Chihuahua or some other dog. Also, a very well-known operation is called pooling. So pooling is a quite simple operation. So basically you have one parameter, which is called the size of the kernel. You have here a size of 2 times 2 pooling, and you just move through the image again. But for example, for the max pooling operation, you just pick the maximum value. So if you look at this lila or a purple rectangle. Here, the maximum value is a 3, so you will just pick the 3. You then slide your kernel to the left, to the right, and then you will pick again your max value and so on. There are other operations like mean pooling, average pooling, and a few others. But that's, I think, the basic understanding of these two very important operations, convolution and pooling. Right. What are the current state-of-the-art architectures? So one of them, it's called BGG16. The 16 just stands for the number of layers that are present in the network. And here, yeah, basically you can see just the same operations as I explained before, a lot of convolutions and max poolings and so on. Just one small note, so you can see here, I hope you can see my mouse. You can see here the image size, so you have 224 times 224 times 3, so the 3 are the color channels. And you may ask, okay, we have nowadays pictures with very high resolution. Why do I see always such small sizes? And I think that the first answer is that it is infeasible to compute or to have inputs which are very big, just because there are a lot of computing operations that need to be done. And the second reason is actually that if you think about a high resolution picture, and you just take some part of the picture, and then a lot of pixels around a certain pixel are just equal, just because it is a very high resolution. So there is actually not a really big problem to just downsampling the image. Then we have something called, here you can see actually a comparison of VGG, some plain fully connected network or convolutional neural network, and something called residual neural network. I will just skip the details, but you can see, I think, it's getting more operations, more layers, even deeper and deeper and deeper, and that's also the reason why it's called deep learning. All right, let's dive into advanced applications, or actually which application can I solve with computer vision. As I mentioned before, image classification. So taking the Chihuahua example, the task is just to predict if there is an object, a certain object in the image. We have then object detection and localization, similar task, but instead of just predicting if there is a dog or whatever object in the image, you also want to localize it. So you want to really specify where it is located. We have also image segmentation. So basically, distinct certain regions and highlight the regions of certain objects in an image. Facial recognition, I think nowadays nothing fancy anymore. Sentimental analysis is something also quite cool. So basically, just trying to predict from a picture what are the emotions of a person. Is the person angry? Is it happy? Is it sad? And so on. Visual understanding, especially here in healthcare, I think it's something very important, and we will start seeing more and more applications. So yeah, just recognizing certain patterns in an image. Augmented and virtual reality, robotics and automation. So basically also in industry applications for quality control, or really to recognize certain parts of a mechanical object and so on. Also something very important today or nowadays, environmental monitoring. So basically taking satellite images and just gain information from these images, something very important. And that's basically it. Now I just brought you some demo, and I would like to conduct this demo with you. For that, I will just slide to the right. I hope you are still able to see my screen. I encourage you to just try it by yourself. So it's called the Teachable Machine. And here what you can do is you can just train a neural network on your browser, on your PC, very easily, just to get an idea of how it works. Let's start with this example. So we are now, we can train our model with 2 classes, or you can actually add more classes. And for that, I just it's actually here. I just borrow something from my son. So he's a big fan of Paw Patrol. Maybe you recognize that's Marshall and that's Chase. And now we will just train a neural network which is able to classify on the one side Marshall, and on the other side Chase, or actually the other way around, I guess. So let's start with that. I think I will just go a little bit to the side. So what we will do now is basically just collect some images of Chase and some images of Marshall, and then just train the network. So if we just start, so let's move a little bit to the side, maybe from the back. Okay, I think that's enough. Let's call this Chase. We'll then train on Marshall. Basically the same procedure. Let's take the webcam, just go a bit to the side. So a little bit here. Right, now that we have some images, we can just start training. I will just leave this, all of the settings default. I think it should be fine. And now it's actually starting training. So basically a convolutional neural network is training in the background. And yeah, hopefully it will be able to just classify those images correctly. Let's see. So it should be done in a few seconds. All right, it's already done. And now you can see, so I'm in the image and it's already predicting that it's Chase. Maybe I look a little bit like Chase, I don't know. So as expected, Chase. Let's try Marshall. Yeah, it's actually working fine. It's Marshall. Of course, I'm not Chase. So what we also can do, we can just retrain the model again and just add a new class. And let's call this class, I don't know, none of them. And yeah, let's just take some pictures, maybe without the background and so on. Now, I hope it will able to classify them correctly, if it's Chase, if it's Marshall, or none of them. All right, let's try again a little bit. Should be done in a few seconds. All right, so, and you can see, yeah, it's actually predicting none of them as expected. Now it's Marshall. And now it's Chase. Nice. That's really just a small example. So I encourage you, again, try it by yourself just to get the sense and to play a little bit around with such neural networks. Okay. Conclusion. Yeah, I hope I could show a little bit and give you some information about computer vision. What is computer vision about? I hope it was interesting for you, and I will be happy to answer your questions.
Thank you, Fabio. And if somebody has, who are following now us and watching on Facebook, any questions, you can really write it and I will just read it out loud here. And if not, I mean, or before other questions come, I was wondering, you know, one thing how we usually imagine artificial intelligence, or what we hear, like, you know, in a soft pop level. I mean, we imagine as all, maybe we know, we meet the final results, you know, like facial recognition, some object recognition, and so on. So one thing is how we, as simple people who don't have, for example, any experience in IT, imagine that. But from your perspective, what a person should be interested in or know very well in order, or like with a goal to study, or like artificial intelligence. I mean, what is important in your opinion to know? Maybe some IT languages, I don't know.
Well, that's a good question. I think first of all, you just need the motivation, first of all. So I think independent of the background. So I don't think it's dependent of some background. So first of all, you need real motivation for that. And of course, it's always easier if you have an IT background, just because a lot of these tasks are IT related. Definitely also some mathematical background is good, just because I think 99% of those operations are mathematical operations at the end. And it makes, of course, things easier. Just if it doesn't work like you are expecting, then to know how to debug, to understand what are the mathematical principles behind it, as I showed before, what is a convolution, what is a pooling. And I think, yeah, that's basically the skill sets. I think it's needed, but first of all, you just need to have motivation for that. All the other things, I think you are able to just learn. Yeah.
I think, thank you very much. I have, I think, some questions related to what you said now. So what kind of IT tools is it? I mean, probably it's what should a person know? I think that was about.
Can you hear me?
Yeah.
Okay.
So what kind of IT tools is it? Is it what you meant about
IT tools? So basically, I mean, a lot of stuff is doing, I think you mean maybe the technologies which I use. So I use a lot of Python. I think nowadays Python is, I would say, the most known language, especially in this field of artificial intelligence. You can also use other languages. That's, I think, not a big deal, but I think just for someone which starts with artificial intelligence coming from a different background, I think Python just makes things much, much easier. So you can quickly just rapid prototyping certain things in Python, and the languages you will need to know about compilers and all the other stuff. So I think Python definitely is something you need to know nowadays for those tasks.
I hope this answers your question. And if not, you can always ask once more. We will see your question. Thank you. At the moment, I think we don't have any questions related to your presentation. However, we can always talk a little bit more at the end of the second presentation, just to close it. So thank you very much, Fabio. And
thank you.
Now we will give a stage to our colleague, Gustav. Thank you for joining us. And I hope that Gustav will tell you a little bit more about it. And if you have any questions to him, you can always ask. Gustav, you will present yourself as well, probably.
Correct, yeah. Give me a second. Yeah, all right. Can you see my screen? Good. So what I will talk about today, I will give you a quick introduction into generative AI and large language models, and how to overcome some of the limitations. Nice, just like a typo in the very beginning. So some words about me. I'm a senior machine learning engineer at DataRobot. So I'm developing an automated machine learning platform, and I'm doing machine learning engineering since 2017. So it's now roughly 5-6 years. Yeah, I'm coming from Munich, born and raised there and living there as well. And yeah, that's all about me. Let's get started. First, I want to demystify generative AI, just to get an understanding what is it and what is it's not. So generative AI leverages machine learning models to produce various of data outputs or data types, so text, images, audio, video. And main models used for generative AI are large language models, LLMs, like GPT-4. Maybe you heard of that. That's the model which is powering applications like ChatGPT, which currently are very popular. And they are a particular type of models for generating text. And typically, they are trained to predict the next word in a sequence of text. And applications, as I said, is, for example, ChatGPT, which is then fine-tuned, is like a fine-tuned LLM on specific tasks, for example, question answering. So on the bottom, you see some example models like GPT-3 for Llama, which is the model of the Facebook mother Meta, and DALL-E, which is a model for generating images. Some example applications are ChatGPT, GitHub Copilot, which lets you or assists you in implementing writing code, Bing Chat, which is like a superpowered search engine. Bard AI is like ChatGPT, but from Google. And Microsoft 365 Copilot is a Copilot or an assistant for all Microsoft Office applications, for example, for Excel, for Docs, for PowerPoint, which lets you, chat with it and generate content. And what does it mean when I said like it is basically predicting text or like the next word given a certain input text? You see here in the gray box for an example input of what is generative AI. It iteratively predicts the next tokens. Tokens can be a word, or can be a part of a word, or can be multiple words. So it's just a unit in which the model operates. So the first token would be, which it predicts generative AI, then generative AI then is a machine learning field, and then says, okay, this is the correct answer, and that outputs the generated text. Generative AI is a machine learning field. But it didn't come to this conclusion at once, but it was like iteratively predicting the next word and until it comes to a complete solution. Then quickly, I want to talk about different types of generative AI models. So there are mainly 3 different types. Remote pre-trained models, which can be accessed through APIs. For example, OpenAI, Lambda offers those. The pro is they are most of the time the most advanced one because they are hosted. The cons are sometimes high latency, and of course you need to pay for them, so consumption costs. And often they have some data security topics because you send the data to these companies, and often they will use it again. So you shouldn't use sensitive data, for example. Another model family are open source models or third-party pre-trained models. They are often specialized models and are released with a certain license. So it could be that you may use it for personal use or even for professional use. It depends on the license. This is also one of the cons. The license can be restrictive, and often it's necessary to manage your own data and the compute because they are not like a full service like the first model family is. The third model type is models developed from scratch. This is basically only possible for big companies who have the capacity and the know-how to do this. And even for small companies, it's not possible to develop these models from scratch and train them from scratch, especially because collecting the big amount of data and training it is really complex and needs a lot of know-how and is very expensive. And yeah, in compute resources, but also in human capital. So those are three different types of generative AI models. And now I want to give you a quick breakdown again on LLMs. So they are deep neural networks, what also my first presenter, Fabio, presented. They are based on the transformer architecture. This was introduced by Google in 2017. Here's the link to the paper. I will talk about that later. And what is important is they are trained in two stages. You just saw in the first presentation what training is. So you train the model, for example, there in the demo, Fabio did it on images. And here it's trained on a large fraction of the internet. So the internet is scraped in text, and then the model is trained on it. This is the first step. After the first step, the model is capable of really good text prediction. So it has a good understanding of text, and given a certain input text, it will predict how the text proceeds, basically. So if you, for example, give it like the first half of a book, it would predict the second half. That's what it does, basically. It just continues what it gets as input, and it's really good after the first stage. The second stage is then fine-tuning on a specific task, often with human feedback, which is called reinforcement learning with human feedback. And how does this work? After the first stage, you want it to specialize on a certain task, for example, question answering. And then you prepare a data set with always question answer pairs. And during the training, you feed the model a lot of these examples. So it understands, okay, if a question comes first, I need to reply with an answer. And then it generates an answer, and the human then checks, is this answer what I want? And if it's good, it gets a plus, basically. And if it says this answer is bad, it gets a minus, and the human corrects the answer and feeds it back into the training. This is the human feedback here. It's of course expensive, because paying the humans and not doing it automatically is expensive. And that's just another reason why training those models is an expensive task. Then, yeah, another point is these models are extremely large, like 100 billion parameters. For example, the computer vision models that Fabio presented have maybe some million parameters. Here we're talking of billion parameters. And for example, OpenAI's GPT 3.5 has like 175 billion parameters. And for those models, most of the time, bigger is better. At least until now. This can change, but until now, the bigger is better. And as I said, the basic functionality is really predicting next words based on given text. And this can be applied after fine-tuning for many tasks like bots, which is question answer, information extraction, which is like summary, for example, instruction following, like say, you get tasks and complete those tasks, or full automatic agents, which can do all of that together. And of course, many more applications are thinkable with this. And then I want to talk about some important properties of these models. This is just some internal parameters of the model which define basically its capability and how it works. So the first parameter is the vocabulary size. The vocabulary is like the word, like how many words has it been trained like on unique words. So for example, all the words that you know, the unique words is your vocabulary, and that's the vocabulary it has been trained on. For example, GPT-3 has a 50,000 vocabulary size for English language. This is just English. Other languages is different, of course, and GPT-4, 100,000. Then the context length. This is the maximum number of words it can process with one input, so at once. What is the biggest question basically you can ask? This is a highly limiting factor, because of course, if that's bigger, it can process much more text in one step. Then the next, for example, here GPT-3 has 2,000 context length, and GPT-4 has 2 versions with 4,000 and 32,000. So quite a big step here again. And the next important property is the number of parameters. This is basically telling us how complex, how big is the model, how strong it is in computations, but also how expensive it is. And GPT-3, for example, has 175 billion parameters, and GPT-4, this is just estimate because they didn't release numbers on this, is estimated between 1 and 100 trillion parameters, so huge. And the final inherent model property is the training tokens. This tells us how many words, not unique, but words in total, has the model seen during training. This is just telling us about the training data size basically. And for GPT-3, this was 300 billion tokens, and for GPT-4, there is no number and no estimate released. It's just estimated to be roughly 500 times as much as GPT-3. So yeah, a big step here again. And finally, I want to talk about temperature. That's not something that's defined during training, but during the usage. And it controls the randomness in the next word prediction. It's a value between 0 and 1. And the bigger it is, the more random the predicted words are. And if it's close to 0 or 0, it's absolutely not random anymore, and it's therefore reproducible. And to understand what this means, I mean, as I initially said, the model always predicts the next word given on the already seen word. So it predicts the first word, then takes the first word again, predicts the next word, has those two words and the third word, and so on and so forth. When the temperature is 0, it will always just pick the most likely word, and those will always be, of course, the same chain of words. But if you introduce a randomness, the temperature here, and this can like increase up to 1, then it does not take the best model or the most likely word, but for example, the second or third or 10th. And like with introducing this randomness, the resulting text can be anything. Of course, you start with the same word, maybe, but then it can result in something completely different. And therefore, the result is not reproducible anymore. That's something you might see, for example, if you use ChatGPT. If you ask the same question 10 times, you get 10 different answers, because the temperature is normally set to something around 0.7, for example. All right, and yeah, coming to the next slide, which is just showing again like how the size of these models increase. So the evolutionary elements, you see 2017, the transformer was introduced, and now we're even further in 21, which is like GPT-3, and then it comes the Google Switch transformer with 1 trillion, and like GPT-4 is like even further up, and you see like NLP's Moore's law is there. With every year, the size of these models increases by the factor of 10. Now I'm coming to some limitation of these models. We just saw how they work and what they're good at, but they also have some quite important limitations. So first of all, these models are only trained up to a certain date. For example, OpenAI models up to September 21, which means they have no knowledge about recent events or anything that happened after this date. And it's important to know that these models are not learning while they are used. So if you're chatting with them, they're not increasing their knowledge. That's just usage. Training has happened and it's complete. And at some point, OpenAI will retrain, and then it gets updated to a new date. But it's like, since then, it hasn't learned anything. They're like playing patches and stuff on top of it, but it's not really like the knowledge of the model increases. So that's important to know. And also, it doesn't know, of course, about documents or text it didn't see during training. So if you're a company, for example, and have private documents about your processes, it can't answer questions about these if it hasn't seen them. That's important to know. And then, as I already said, the context window is a important limitation, because it limits the maximum length of the prompt. So the question it can process at once. And then 2, often cited limitations by the media are one, hallucinating. It means that, sorry, the model can make up answers. And that's just true because of the fact that it has no inherent understanding of what is true or false. It just knows what is most likely, because it's just always predicting what is most likely to come next. It's a probability. So there's no true or false. It's like 90% this should be the answer, but it's not like that's a fact or not. That's just not how these models work. And that's important to keep in mind. And furthermore, they can give biased answers. And why is that? That's because the data it was trained on, the internet, is full of bias. So of course, you can sometimes get answers that may be racist or have some other tendencies which are not okay. But the reason is not the model because the model is somehow racist. You could say this. It's just the data. There are like problematic informations available in the internet, and it has seen this and it repeats this because it's just like, oh yeah, it's quite likely that such an answer is the right answer because just the internet is full of such stuff. So an important question is, how can we overcome some of these limitations? And therefore, I'm coming to a certain use case, which is the knowledge base. And we will also later see a demo on this. So it's important now to understand how this works. It's basically split in two phases. The first phase is the ingestion. It works by the document. You have like certain documents, for example, your company documents or your private book collection or anything that you're interested in, maybe episodes of your favorite podcast or whatever. And those documents are then split into chunks. So they are split into right sizes because the document can be any size, but as we know, the models are only able to process a certain length. So we cut it into chunks. Then these chunks are encoded into embeddings, which means we produce vectors out of text. Vectors are arrays of numbers. So a list of numbers, for example, before you had a sentence, which is characters, words, strings. And after this encoding, you have numbers basically. So those embeddings are then stored to a vector database. And then the ingestion phase is basically finished. And now the usage can begin, the inference. And how does this work? A user submits a question, for example, via a chat window. Then this question is encoded into embeddings, just like in the initial phase. And then the most similar embeddings are searched in the database. So you have the question, and now you compare it to all of the embedded text chunks. And the most similar ones, that's just a mathematical computation. The algorithm that does it is called k nearest neighbors. So you get like a certain number of most similar text chunks back, like embeddings. And these embeddings are then decoded again into text and combined to a context. And then a prompt for the model is built from this context together with the initial user question. So the prompt could then, for example, look like, given this text context, which is like the decoded embeddings, try to answer the question. This is the whole prompt, and this is then fed into the LLM and is queried with a prompt on the temperature 0. Temperature 0 is used for this case because we don't want it to make something up and we wanted to generate reproducible results because, of course, like an app, if you would use it in a company and you search for how internal workflows work, you always want to get the same answer, because if one employee, for example, asks the question and gets like one answer and the next one gets a different answer, that of course could lead to issues. Therefore, for those applications, you set the temperature to 0. And then the last steps is the LLM generates, as I said, reproducible responses, and this answer is then fed back to the user and he gets the answer. So this is the full process, basically, how knowledge bases work. Leading us to the application that I will present you. It's DataChat. That's an application I implemented to learn the technology basically during the last weeks or months. And what it does, it lets you chat with any data source. So for example, code repositories, books, websites, financial reports, tables, and many more. And it's an open source implementation. So the source code is free. You can go check it out. It's implemented with Python, LangChain, OpenAI, API, DeepLake, and Streamlit. So now let's go to the demo. Hopefully it will open. It's not overloaded because that happens from time to time. We're here, good. So this is the login, basically. You need an OpenAI API key. Here on the question mark is some links how you can get such a key. I got mine saved, and then we are basically good to go. You can also specify an active loop token. That's a token for the database, but that's optional. If you don't have such a vector database, you can use the one of the app. Submit, and we get authentication, and now we are able to query the app. And the app is built like this, that we can right now already post questions. And of course, the question is, what is the context here? We are like, what is the knowledge base? And I implemented the app like this, that its own code base, it's its knowledge base. So if I ask now something, for example, what is this project about? It reads through its own code and tries to answer the question. So the answer comes not from OpenAI or ChatGPT, but it's based on the code that I've written. And now it's generating a response. We also see here the usage, how many tokens have been used, how much does this cost? Because of course, as I said, so the hosted solutions of those models are not for free. And here's the response. It says, this project is called DataChat. It's an app that allows you to ask questions about any data source by leveraging embeddings and so on and so forth. Just what I already explained to you previously. And now we can also input a new data source. For example, this is the paper attention is all you need. It's the initial paper of the transformer architecture that Google introduced in 2017. I already mentioned it. And now we can just, for example, here, paste this link, hit enter, and now it builds the chain or vector database for this document. It's loaded, and now we can ask questions about this document. What is this paper about? Again, just a high-level questions because we just want to see if it works. Hopefully, we get now an answer not about DataChat, but about the paper. And the paper, now it says, this paper presents the transformer, a sequence transduction model based entirely on attention, which is used to achieve state-of-the-art, blah, 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 so on and so forth. So now we are basically on another knowledge base. Now we can query this document, this PDF paper. We can ask more questions, more specific, for example, how was the training performed? And now we wait for the response. And here it is. It gives us an answer about how the training was performed with GPUs and number of hours, number of steps, because that's something that has been written in the paper. And yeah, that's the application. You can try check it out. The only thing that you need is the OpenAI API key, but you can generate it. You need to know, of course, the usage of this key costs something for you, so you will be billed. But as you see now, those questions that I asked cost me in total 1.5 cents. So it's not that much, but of course it's not free. And you can also, if you want to use it, either paste here links directly, or you can browse files on your machine and then, for example, upload one or multiple files and then ask questions about it. Yeah, and that's basically it.